why so many people today? It's because we decided like to skip some chapters and jump into the zero knowledge parts proof part. So we will be talking about Starks and how they work. And luckily with that, we can start working on other proof systems or things related to Starks. And that's why we also have like a large part of some people from Lambda also joining the meeting. So the idea, as always, is to present the topic. We are going to give an overview and then maybe give like some supplementary material and all that. But we were going to do one thing, but then we thought and said, okay, why not start with uh, validity proofs? So
Yes, and to add something, so we will soon be starting to make teams and start coding uh, on the repo. Some people on the Star protocol, maybe some other people on Soundcheck, improve things, add things, some hashes that are missing. So the idea is to first have an overview of the protocol and the code. Some things you won't understand probably because it's going to be a lot for one day. The other commentary is that it doesn't matter. I don't know, one of our best optimizers of the code doesn't do cryptography. Uh, and probably doesn't know how the protocol works. He's great. And the same is going to start to happen. Some people will be really good at maybe understanding hashes, but they won't understand the proof of Fry, and it's going to be okay. You don't need to understand everything to collaborate with the protocols.
so yeah, we skipped like several chapters and now we are jumping into fun. So that's why we had this first discussion on polynomials, the FFT, and all that. And after this talk, we have like some interesting news about upcoming talks. So without further delay, let's jump into Starks. And so here, so we are talking about Starks, and these are related to something called validity proofs. And the idea is that we can show the integrity of some computation or we can verify because show we can verify the integrity that would be like so let's use the correct word verify the integrity of some computation in a much faster way than trivial verification.
Here, for integrity, it means like we are going to prove to someone that we executed some algorithm. That's the thing we are trying to prove. Uh,
Yeah, and the thing is, you always have like the trivial verification, which is just rerunning the code on your own. But for example, very large programs, that could be infeasible. So having a way of verifying a program is really important, and this has applications in scaling, for example, Ethereum.
because the usual way to work with Ethereum will be like that trivial verification. You need to execute in the VM all the nodes to execute the code of the transaction or the token transfer or whatever. So in a way, this is a more efficient way of doing the same.
So now we have let's start with the execution phrase. It will be a table containing the values of each register for each time. So we can imagine this as, okay, this is register 1, 2, 3, register N, and then we have here like the clock time, and so 0, 1, 2, 3, 4, until n. So, of course, each of these will have like several values. And so, what would be like the way to prove that we did the computation properly? So, well, we would have like to show that, okay, this has been initialized with the correct values. And then there will be like some way to show that if we started with the values at time 0, then there is a way to show that we applied like a certain function. And so that the values in T1 are dictated by the correct update function. And then, of course, we could do something and show that, okay, then I move to T2, to T3, to T4, and so on and so forth. And well, of course, then we get like to the final result, and maybe we want to check this result.
Just to add a little bit to this, because the idea is how do I prove to you that I have executed a program or an algorithm or whatever. What I'm going to prove to you is all the intermediate values and that I have applied all the right operation in each step. There will be like two ways of doing this. One is with a VM. These stars will be more adapted to work with VMs, where will we define like a computer over this. I don't want to dig that in that right now. Or you can just make like a custom thing for each step. Okay, we will dig into that later. But think of these rows as all the intermediate steps that are going in the algorithm, and you have to prove all of them, because if you don't prove one of them, maybe that step was wrong.
So,
I'm trying to understand a little bit, right? What are the R1, R2, R3, Rn, right? And what I imagine is those are like registers, and you have finite set of operations that change the set of registers to the next step. It's like that?
Yeah, that's a way of thinking it. Right now, let's pretend maybe this is something really easy. Maybe it's just Fibonacci, and in each row you have like 0, 1, 1, 2, 3, 5, 8, and so on.
yeah.
There is some way of saying, okay, the next value should have respect this constraint. Uh,
So we can have something like even an easy function. So what we want to do is f of x is x squared. So what we do, this would be a sequence where xn plus 1 is simply xn squared and x0 is just 2. So here I have 4, and this is 16, and then this is 256, and so on and so forth. So here it's easy to show that the computation is valid if I can show you that I started with 2, and then that each value is just the square of the one that's already before. So what we're going to try to do is to introduce a notion which is of something called the algebraic intermediate representation. So here I have like these values, and if I want to show that these values are valid, I have to show this first value, this first constraint, which I could, for example, go and check the value at the first register and see whether it is true. And then what I can see is that the relationship between any two consecutive values, I call the current value x and the next value y is given by the following equation. It's y minus x squared is equal to 0. So what we can view is this restriction can be interpreted as a bivariate polynomial. Yes, a polynomial in two variables with this formula. So the constraint is valid if for every pair y and x that I choose, p of, well, let's say y0, x0, x0, y0 is equal to 0. So I have to show that I take any two pairs and then I plug them into this polynomial and it evaluates to 0. This polynomial is called a constraint polynomial. Of course, there are like different types of constraint polynomials, but this is just to have like some terminology because then Starks always mentions like constraint polynomials, and so these are just the polynomials that dictate how the computation evolves at each step. We will see that we can have like more complex cases, but let's focus first on this very simple example. Are you going to say something?
No, no, no. Go ahead. It's perfect.
So how can, okay, so how can we show that this constraint is valid for every pair? So we have to show that this is true for the first pair, and then for the second pair, and then for the third pair. So we see that we are in kind of some problem because we would have like to take all the values of the table and then plug everything in. And so the problem is my verification is more or less the same as just re-executing the code. So this is where we will try to make polynomials appear. So what we are going to do is we have this table of registers, 2, 4, 16, 256, and say, okay, these values correspond to evaluations of some polynomial. So there is some t, for example, we say 0, 1, 2, 3, and we can say that there is a polynomial f of x such that f at 0 is R0, f at 1 is R1, f at 2 is R2, and f at 3 is R3. So you know, like this problem, it's just what we call polynomial interpolation. So we want to have a polynomial that evaluates to the different values we have for each register. And these polynomials will be called the trace polynomials. For each register, we will have one trace polynomial. So we have to do interpolation because nobody is forcing us to say, okay, you have to evaluate at 0, 1, 2, 3. What we can do is choose convenient points, and perhaps the best thing is to choose the what we call like the roots of unity. So in this case, because we have like 4 values, we can use the 4th roots of unity. And so if you remember, these have like a generator omega, and the roots of unity are just given by omega to the I, such that I is equal to 0, 1, 2, 3. And so this will be our domain. We will call this the interpolation domain. So because we are using like this nice domain, and so what we are doing here is say, okay, no, this t is just 1 omega omega squared omega to the cube. What can we do to interpolate very fast? Of course, what we can do is use the FFT. So we can use the inverse FFT to obtain these trace polynomials. And just to keep with names, I will call these T of X. Yes? So what we now want to do is kind of enforce the constraints over the trace. So we have this polynomial p of xy, which we want it to be like 0 for those pairs. So how can we take a value xn and then take the corresponding xn plus 1? Well, this is a nice trick because we are using like roots of unity. It's just, okay, I take, okay, t of x. So if I evaluate at some x, I have like the current value, and the next value is
Diego, sorry, I missed something. What is T? Because there was above was F, right? Now it's T. And T is in the on this new domain, right? Oh, okay.
Yes, I prefer just for it to be like T of trace, so that any problem. So you can see that by doing this trick, I get all the numbers, because if I say, okay, T of omega, which is 4, I look then for T omega squared, and this is 16, which is the next value, and then I say, okay, T of omega squared 16, T of omega cubed is 256. So this trick, what it does is it allows me to get like the next value. So if I want to say that this evaluates to 0, what I am trying to show is that P of T of x, T of G of x, oh sorry, G, no, I always use G, but omega, this is equal to 0. So what I can do is like obtain this polynomial, plug it inside, and show that it evaluates to 0 for any value of x. Here it should be valid, of course, for x equals 1 omega omega squared. Yes, this is because we only have like one transition, which is from 0 to 1, then from 1 to 2, and then from 2 to 3.
This statement that Diego has written there, you will see it on the code of the prover. We will not show that to the verifier, but since we have like a lot of constraints, a lot of columns, a lot of data, what you will see in the prover is that we do this to kind of debug when we are exploring new architectures. And if some of these equation doesn't hold, we know that we actually inserted the bug. We need to fix something in the constraints or how the trace is generated. I think someone asked a question. Yes.
About, omega.
Yeah.
Roots of unity.
What does it say?
Can you elaborate again, please?
Omega is just what's called a primitive root of unity. It's an element that if you take all its powers, generates the entire group. For example, I will show it for the complex numbers, but the same thing works for
it's just like an optimization for the Fourier transform. You could just pick 1, 2, 3, 4, and whatever, but then it's going to be really, really expensive. So you need this to be able to apply the entities or Fourier.
Yeah, so this is in the complex numbers. One of the 8 roots of unity. And so if I take this element, this is just my omega, when I multiply omega times itself in the complex numbers, it just amounts to a rotation. So I get this element, and then this element, this, and this. So this is a generator of this group of roots of unity. It's just something that you take powers and it generates all the elements of this set. And you need this to be able to do the FFT. And the FFT is just used for efficiency, nothing else. So how can we show that P of T of X and T omega X is equal to 0 over some set D prime? Because what we wanted to show is, okay, I take...
Diego, sorry. Why omega times x? In the why change of variables? You have x
no.
and you have omega times x.
Yes, because the polynomial, what it does, it needs for you to supply the current value and the next value in the table. So if I am taking a value at, say, x equals omega, what's the next value? It's omega squared because of the structure I chose. So that's the way of saying this will be my x, and this is just a way to get y. I know it's very confusing at first when they tell you why you just plug omega x and it works. It's kind of weird, but it's the way like of grabbing the next value.
Yeah,
For this function, right? It's not in general, right?
No, it would be in general because the thing is these elements are just powers of omega. So if you are in any omega and you want to move to the next, you have to multiply by omega.
There might be cases where that's not true, but let's wait for the end.
Yeah,
For
of
that.
course, some computations, the thing is you may have to supply more than 2 consecutive values. You may need to pass 3, 4, or something. But those have to do mostly with ideas in how they implemented the START protocol. But in principle, for any computation, it should suffice for you to show, okay, I was in this state, I applied some function, and now I got to this other state. So we have this. So we want to show that the polynomial evaluates to 0 over some set D prime. So in this case, the set D prime would be 1 omega squared. Why? Because what I want to show is the transition from the initial state to the first state, and then to the second, and then to the third. And so we have to do this. So the thing is, of course, I could take all the values of omega, plug them inside, and all that. But the problem is, again, I have to evaluate as many times as points I have in the trace. So it's not succinct or shorter. So here is where an interesting property of the polynomial comes in, which is polynomial division. I think I showed you this, but if P of x is equal to 0 at x0, then P of x is divisible by x minus x0. What this means is if you take P of x and you divide it by x minus x0, this should be a polynomial Q of x. So this should be a polynomial. Of course, if it does not evaluate to 0, this should not be a polynomial if P of x0 is different from 0. So what I can do is, okay, I have a polynomial C over D prime of x, and this polynomial is just given by the product of x minus omega to the k, for k 0 to 2. This polynomial, the interesting thing is that d prime at any x0 is equal to 0 for every x0 in d prime. So this polynomial is equal to 0 at every point over the set where I need to enforce the constraints. So in our case, this polynomial is simply x minus 1, because at 1 you enforce the constraint, x minus omega, because you enforce, and x minus omega squared. So this is the polynomial, and there are like some tricks to be able to evaluate this polynomial like really fast, because in fact this polynomial can be seen as x to the 4 minus 1 divided by x minus omega cubed. This is just a trick, a cool trick to be able to evaluate this polynomial. This polynomial in general is known as the zero fire or vanishing polynomial. So now that we have introduced this polynomial, the way to show that the constraints are valid is show that p of tx t omega x divided by this polynomial is a polynomial. So if I did everything right, this quotient should be a polynomial. If it's not, then some of the constraints are not enforced. So what I have to do is kind of convince the verifier that this is a polynomial. And this is like the tricky part. So remember, I do this composition of polynomials, and this is just a polynomial in one variable. This was P had two variables, but then I plug these two, the trace polynomials, and this just becomes a univariate polynomial. So if I can prove that they are divisible, I did things right. If not, I am cheating. So far, have you understood everything? Do you have any questions? So here comes like the tricky part. How can I show that this c of x divided by this is a polynomial? Well,
We have a question. I got lost when you explained the zeta d. May you go again? The yes,
The zero fire.
yeah, the zeta
Yes.
fires.
yes, we need to show that p of t at 1, t of omega is equal to 0, which is just like evaluating this constraint at 1. Or just, I call it C, this polynomial, so this would be C with x equal to 1 is 0. But then I have to show you that C t at omega t at omega squared is also 0. This is x equals to omega. And then, of course, again, omega squared and omega cubed. This is 0, and this is just x equals omega squared. So the thing is, I need to prove that the polynomial is equal to 0 at 3 points. And so
that part is like saying this is where I codified my data. I have this big polynomial. It's more obvious for me not in star but in stars, where you have codified data of the trace in the polynomial, and one of the statements is okay. Each statement is codified in these positions, and the position where I codified in the encode is not codified. Where I encoded the data is 1 omega and omega to the 2.
So what I have to show is that this polynomial has zeros at x minus omega, x minus omega squared, and x minus 1. So this means that, well, c of x should be precisely x minus 1, x minus omega, x minus omega squared, times quotient. So this is something we talked when we discussed polynomials, that you can factorize the polynomial into lower degree polynomials. And so what we are doing is, okay, if this polynomial is right, then it should have all these factors. So that's what we are doing, and we call this polynomial, which is simply the places where you want this polynomial to have zeros. Of course, your polynomial has zeros if and only if you did the computation right. So how can you show that this is a polynomial? Of course, there is like an easy way. Just send all the coefficients, and well, then someone could like use values from the trace to show that, in fact, at some places you did the computation right. So that could be one way. That is to say, I give you a polynomial that I claim this polynomial is the one that represents the enforcing of the constraints over the trace, and then of course you say, okay, I want to check, I take some values, do some calculations, and show that it is correct. So
you could also try like to query the prover, say, okay, give me a point, give me 2 points. Now I start to trust you. But even if you do something that is probabilistic and you ask for some points, there's always a chance that one of the points is wrong, or that some value you have not queried is wrong. So by doing all of this, we will reach like a much higher level of confidence on the prover.
So what Mauro says is, for example, we could prove this interactively. And this in general, of course, this proof will be probabilistic. If we want to be 100% sure, we would have like to test all the values, and then of course there is like no gain. But what we could do is, for example, have some verifier say, okay, choose at random any point in the table, and then the prover will supply those two values, and then the verifier is going to check whether it obtains the same value as the polynomial they say. So what he would have to do is kind of, okay, I take omega k plus 1, I subtract omega to the k squared, and then I divide by some signifier evaluated at omega to the k, and this should give the same as what the prover says. Of course, here there are like some problems that I will jump a little wide, but let's for now just wait here. So we see that we have a big problem, because if you have to send all the coefficients and your computation is really long, we have to pass like 1 million coefficients or more, so that's not practical. So instead of doing that, what we are going to do is introduce some low degree proximity test. And this is where the Fry protocol comes in. Fry protocol is just simply fast read Solomon interactive oracle proof of proximity. So what Fry allows us to do is, okay, we have like a certain function, and we can show that that function is close to a low degree polynomial. So what we can do is kind of, okay, I have like this thing which I would like to be a polynomial, and so I can use this Fry testing to show that that thing is indeed a polynomial, or it is close to some polynomial. So how can we do that without having to send all the polynomial and do the test? What we can do is, instead of
Yeah, so they are asking what does close mean. Okay, so this proof, we won't go into detail in how the proof of this work, but it is, you also need to make sure that the polynomial is of certain degree, because the validity of this holds only if the verifier can check the degree of the polynomial, or at least that it is close to some degree. If it is really high, this doesn't work anymore. So that's why this is close, and it's as close as the verifier needs, but we are not going to dive into that here.
So
yes, in summary, you want to check that certain function is a polynomial. That's all what Fry wants to achieve. Like in the mathematical terms, you have to say like it is close to a low degree polynomial and that. But for now, let's say that you want to prove that it is a polynomial. Some certain function is not a rational function or any other function. It's just a polynomial.
So we have like this polynomial, and we say this is just some p0 x. This is a function. So how can we show that this is in fact a polynomial? We know that polynomials have like this redundancy. If I send you more evaluations than the degree of the polynomial, and it was in fact a polynomial, then no matter how many points I send you, the degree doesn't change, because all the points fall in the same polynomial. So what we're going to use is something I told you, which is like read Solomon encoding. So what we are going to do is, instead of having all the coefficients and all that, what we are going to do is create a table of evaluations of the polynomial at certain points. Why? Because that way we will have an easy way of testing whether the prover did things properly or not. So what we do is something called the low degree extension. And so what we have is a domain B0, which is sometimes called the the LD domain. So what we do is we sample, we get a generator of the roots of unity, and well, this would be 0, 1, 2, 3, until n. So what we do is we get a different generator. So why we do this? Because our polynomial originally had a certain degree, and now what we want is to evaluate over a much larger domain. So in my beautiful drawing here of the roots of unity, suppose I interpolated using this in the low degree extension. What I would do is also add all these values, for example. So now I have like many points to evaluate on. So that's the idea, and this is omega, and this is what I call G. Of course, there is something that is a bit tricky. I don't want to use just the roots of unity. What I want is kind of to shift this, and so I multiply by some h. H is not on the elements spanned by g to the I. So this is an element from, it's called the coset, and it's just like to make sure that the resulting element is h times g to the I is never in the roots of unity. But it has like this very nice structure. So what do we do next? Okay, I have all these elements, and then what I do is evaluate P0 of x at every element in this zero. So what I get is
How do you choose H? Just any H?
it doesn't matter much. In what we use, I think in Starks is 3, because it's a generator of the multiplicative subgroup, or the multiplicative group of the Stark field. It just doesn't have to be in any of the n roots of unity. You need to get an element outside that. So that's enough. So what we get is like this very long list of pairs, evaluations. Um, Now, how can we do to show that we did everything right? Okay, what we can do is to show that we are not changing the polynomial, because the evaluations are a way of describing the polynomial, that we show that we are never going to change the polynomial, is build a Merkle tree. So what we do is simply we take all the evaluations, and then at some point we get this, this, and this. So what's interesting here is I have like this very long list of values.
I can answer that. Right now, we are committing to the points. That's something that we talk about in the last class, maybe. So it's a Merkle tree because it's the most efficient way for then the verifier to query points and for you to show that they are part of the same commitment. That's it.
Yes, that's the way. You have like this very large list of values, but by building the Merkle tree, I just send you the root, and then you can check that I am sending you one value of this Merkle tree. So that's why you need to. So we have like this very long list of values, and so every element here is just one of these evaluations. So this one is this one is here. So what you do is you just do a Merkle tree there. So this is just what we call the commitment. So
And it's just like a point commitment right now. It's still not a polynomial commitment because there are only points. You still have to prove that that's a polynomial. Right now, you can say, I have these values. That's the only statement that is there.
So here comes the framework. So I just I have just committed to this list of values. So what I can do next? Well, I have this polynomial P0 of x, and this can be split into two parts. So we have like the even coefficients and the odd coefficients. This is like what we saw with the Fourier transform. Why this is interesting? Because what I am going to do is kind of project the polynomial and reduce its degree with some trick. Of course, the only problem I see here is, okay, I see that this part depends on x squared and this part depends on x squared. So I could do some change of variables. And if you see, this polynomial has a list of n values, and this has n over 2, and this has n over 2. So what we can do is something like split. The only problem here is like, oh, this x is really bothering me. So how can I get rid of the x? Well, one thing would be ask the verifier for a random value beta 0. And so what I do is I define now a new polynomial P1 of y, which is simply P0 even y plus beta 0 P0 odd of y. So now what's interesting is this polynomial has degree n over 2, because what I did is, if you imagine like a polynomial as a list of values, now with this thing I combined like the odd and even parts, and so I get a list of smaller degree. So that's an interesting strategy. So I started with a polynomial of degree n, and now I have a polynomial of degree n over 2. Of course, there are some things like, why are you so sure that doing this is not cheating? Well, I am telling the verifier, you get to choose any beta 0, and of course, if I am working with a polynomial, this will always work. If not, it won't work. And why do we like this? Simply because of the following. I had my original x were of the form h times g to the I, and now I have y, which is x squared, which is h times g to the I squared, and this is just h squared times g squared to the I. And there is something very interesting about the roots of unity, which is if I have like a generator of the n roots of unity, and then I square, I get a generator of the n over 2 roots of unity. So the thing is, if I define d1 as the elements y such that this is x squared, where x is in d0, the interesting thing is I have size of d0 over 2 different elements. So this is interesting because by doing this trick, the degree of the polynomial is reduced, and also what happens is that the domain has fewer values. So what I can do is, of course, then say, I want to commit to P1 of y. And this is like super interesting because I can do again a Merkle tree by evaluating over D1. And since D1 has fewer elements than D0, the Merkle tree is going to be smaller. So once again, I do my beautiful Merkle tree. I should ask the guys from other companies to help me doing the
You should have it like in the iPad. Some drag and drop Merkle tree. It's going to be useful.
So the thing is, now I have like the Merkle tree, and the good thing is that if I wanted to show that this is a polynomial, I can send you like half the coefficients. I would then say, okay, I want to show that this is a polynomial, so take this n over 2 coefficients, and then you can verify by yourself that this is a polynomial. Of course, there is one thing that I need to show that P1 was deduced correctly from P0. Yes, and of course that gives me like more trouble. But the idea behind Fry protocol is then keep, this is called like the folding, keep folding. So what I do is, okay, I had a polynomial of degree n, I did this trick, and then I got the polynomial of degree n over 2. So I can use like recursion and do that again. So what I do is now I define P2 of Z, which is P1 even of Z plus beta 1 P1 odd of Z, where Z is Y squared. And so I get D2 whose size is simply the size of the 1 over 2, and the elements of the 2 are just h to the 4, g to the 4 to the I. So I instantly see that I can do this all the time. So I can define pk plus 1 of z k plus 1, where this is just pk even of zk plus 1 plus beta k pk of ck plus 1. And I can do this until when? Because at some point it doesn't make any sense. So I do this until I get a degree 0 polynomial. And in fact, if I did things right, this occurs at log 2 of n, where this is the degree of P0 of x. So the good thing is I can, in a finite number of steps, arrive at the degree 0 polynomial, and then I finish. So what I have shown is, okay, from P0 I get P1, and from P1 I get to P2, P3, and so until I get to a constant polynomial. And so because there is like some nice property of this protocol that if the polynomial is near or is far from a polynomial, then it should be far always. So when I do this folding, the distance is kind of preserved. So if in my original polynomial I was very far away, I will continue to be very far away from a constant polynomial at the end. So using this trick, I can show you that it is close to a low degree polynomial. So this is kind of the whole trick of Fry, and at every step what I do is I build a Merkle tree. So the Fry protocol has like zeros. First is when I start with P0 of X. And the first thing I do is build Merkle tree from from evaluations at D0. Then what I do is ask verifier for beta 0, and then what I am going to do is for fold, so I get pk plus 1 is pk even plus beta k pk on here I'd say okay, is x squared and x. So what I do is I just fold. Then 5 get dk plus 1, 6 build Merkle tree for pk plus 1, and then 7 ask verifier for beta k plus 1, and once I have this, now let's do a slight change here. So this is k, and but k is equal to 0 here, and then I ask degree of pk plus 1 is equal to 0. If yes, I just finish. If not, I go back here and repeat. So in general, the thing would be like ask for a randomness, fold, obtain the domain, build the Merkle tree, which is the way of committing, and then I check this polynomial has degree 0. Okay, continue. Until I get to that. So this is like the first part of the FRI protocol, and this is just what's known as the commit phase of FRI protocol. So what I do is I just make this very large list of Merkle trees, so that then the verifier has a way of checking everything, but the prover needs to build all this. So we have to maintain this list of Merkle trees, and the verifier only has access to the roots of the Merkle trees. So I cannot change them. Okay? So next comes like the second phase, which is known as the decommitment. So what we have here is the verifier samples positions in D0. So this would kind of, let me see, this is my Merkle tree, my original Merkle tree, so the verifier can say, okay, I want to query this point. So what I have to do as a prover is show him that I know the value here and that the value is indeed in the Merkle tree. So I have to send him the value, which I shaded in light blue, and an authentication path. So I need to pass this value and this value. This is because if I have these two, I can get to this one, and then with this one, I can get to that one. But the thing is, then to get to the root, I need to pass that value. And so then the verifier can take all those values, hash, and show that it is included in the Merkle tree. So that's a part of the proof. I've shown that I give you one value and you have to check. Of course, there is like, we need like to check that, let's go here. So I chose a point. The thing is, I need to show that I have P0, and from P0 I got to P1, and from P1 I got to P2, until I got to my constant polynomial. So to do that, of course, I need the value of P0 at x0. Yes? But the thing is, I need to show that I can arrive at P1 and then to P2 and then and so on and so forth. So to be able to show that I have correct values of P0 and then I get the values of P1, I need to supply the value at minus x0. Yes, so aside from this value, there is one value which corresponds to minus x0 and say it's here. Of course, when I pass this value, I also need to pass all the authentication. Why do I need these two values? This is something called the collinearity check. And we can do the following. I calculate the value y, which is P0 of x0 plus P0 at minus x0, I divided by 2, and then beta 0 over 2, P0 of x0 minus P0 minus x0. And if everything was done correctly, what happens is this y should be equal to P1 at x0 squared. So if correct, y is equal to P1 of x0 squared. So when I sample this first value here in this Merkle tree, then this value here corresponds to some value in the Merkle tree of P1, and so this could be like this value. There is a way of knowing if I chose this value in this Merkle tree, the value which corresponds in the other Merkle tree is this one. So I can send that value, and the verifier can check that first the value is contained in the Merkle tree. Yes, because I supply the authentication path, and then of course that value corresponds to the evaluations from P0. So this is really interesting because with two values from the layer from P0, I get to one value in the layer of P1 or in the Merkle tree of P1. Of course, then I could kind of repeat the same trick and say, okay, if I have like P1 of x0 squared, and I have also P1 of minus x0 squared, I can combine these two values and get P2 of x0 to the fourth. And of course, then I can do, okay, if I have P2 at minus x0 to the fourth, I get these two values and I get P3 at x0 to the eighth. So what I have to do is for every layer or step of Fry, I need to pass two values, which are pk at x0 to the k, and pk at minus x0 to the k. And this lets me not go down, and of course, the two authentication paths. That way, I can go all the way down Fry to obtain those values. So I can show you, okay, I got from P0, then I go to P1, then to P2, etc., etc., etc. So this is just for one query. So if the verifier chooses at random and all the equations pass, then he knows that I may have done things properly. Of course, maybe I cheated and I got really lucky. So in order to increase something called soundness.
As a side note, with one query, we have a malicious prover that can exploit our prover.
Yes, it's really
really fun.
It's really easy to break if you have one query. So we want to increase soundness, which is the probability that the prover creates a false proof and that it passes. So the thing is, each query has a probability of success of P. So what I can do is, of course, I can ask for more queries, and then the probability of success, every query should pass, and then, of course, this should be P to the n. So if n is sufficiently large,
as one sign of, because some people might not heard about these terms, there are two things that you usually analyze when you improve a system. One is completeness and the other one is soundness. Completeness is the probability that a valid proof will be rejected, and soundness is the probability that the invalid proof will be accepted by the verifier.
Mm-hmm. So the thing is, if the prover has a probability P of succeeding with a false query because he got lucky, then I just repeat that many times, and in order for the proof to be valid, it should pass all those checks. So this is some argument of probability, then the probability that it passes all the checks is P to the n. So we only have to choose P sufficiently large so that the probability is low. So this has to do with the security of Fry, and we can jump onto this maybe tomorrow or some other time, because it's not that easy, because there are many things involved in the soundness analysis of Fry. But for example, some provers said n equal to 30 or n equal to 18. And it depends on a series of assumptions. But the important thing is, okay, the prover needs to ask, or the verifier needs to ask for many queries so that the verifier, the prover sends all those values. So the proof consists of two times the number of queries. Let's say the number of queries is q, so that 2 times q evaluations and 2 times q authentication path. This is per layer. So we have this, and also we need to pass at least
N was like the number of queries. What was n? I lost
number of
it.
layers.
Number of layers. Okay.
Yes. So for each layer, so we had like log 2 of the degree of the polynomial, and we have to pass many queries, and in the Merkle tree they are like logarithmic in the size. So in general, we have like the proof is called log n squared. It's never mind. But we see that we have to pass like many evaluations around that. So this is like the part of the Fry protocol where we need to do all those checks. Of course, there is one thing that I didn't mention and that we also need to check is that this P0 was constructed properly. So we have to check something which is called consistency between the polynomial and the trace. Why? Because I could supply any fake polynomial as P0, and any fake polynomial, of course, will pass. I need to show that this polynomial was obtained from this computational trace. So that's the other check. So what I have to do is I am going to be taking values of P0 at x0, and I will also have perhaps P0 at minus x0, whatever. I need to show that these values indeed come from the trace. So when I interpolated the trace, I got TDX. What I am going to do is the low degree extension of T of X. So what I'm going to do is create the Merkle tree for the trace. So I take T0, the same domain as the polynomial, and then of course I build the Merkle tree, and so that way I committed to this table of values. And so if I want to check the value for this polynomial, then I have to pass some values in this Merkle tree so that the verifier can check that if he takes the constraints and the zero fire and the trace, everything, from this I get to P0 at x0. So this is another check I have to do. So there are checks to prove that the polynomial was built properly, and then to show that that polynomial is indeed a polynomial. So those are like the two big parts of the Star protocol and of any Star prover. Of course, I think it can be like really hard to understand all the details. Honestly, I think it took us like several months to understand it. But luckily, you get to understand it much faster than we did.
As a side note, we have like documentation on how this works. You will see a small difference with what you explained. That there are like, for me, like two ways to understand this. This is like the traditional one. When the Star protocol was created, people didn't talk much about polynomial commitment schemes. And now it's like kind of the bread and butter. You're always talking about polynomial commitment schemes. So you can understand Fry plus these checks that Diego showed to you as a polynomial commitment scheme, and then speak about the three pieces that they usually have, that is like to commit, to open, and to verify. Or you can skip that and just go directly to it, like we did right now. There are two ways of doing the same, more or less. So please check the documentation, see if it makes sense. And if it doesn't, do tell us, and we will try to expand it a bit. And of course, this grows in complexity when you are building on top of it. Well, maybe we can do another day some talk about how to prove VMs, and you will see that this will escalate a bit.
Yeah, we can also dive a little bit on
Wrap, maybe? Oh, no, that's going to be a lot for today, but we need it.
I think that maybe for today we've gone like through many things, but maybe tomorrow or some other day I can go through the code of the prover because.
Do you want to go like today? Why not?
Okay,
We can go to the code. No problem. So you can get a general idea of where is everything. You will see the same things that Diego mentioned.
You'll see that it has like some changes because there are like some optimizations and everything, but it's hard like to explain all this and also say, okay, we have like all this bunch of optimizations, and you say why, and it's just optimization.
Yeah, everything we say is kind of like,
Guys,
it's going to get close.
Guys, can I try to summarize just a big picture of the protocol, right? Just to try to, if I understood correctly, right? For me, you have the trace, and you construct a polynomial out of it, right? Using basically Lagrangian interpolation on the rules of unity, right? That's the first step. Then you forget about the trace because you only have a polynomial. And from the polynomial, what you do is this, then you commit using the Fry protocol. And that's your proof, basically, right?
Yeah, there are two steps. The first one is like the composition polynomial with the zero fire, that you kind of have to prove the relationship and they are okay. So, but then you say, okay, it is okay.
That's an interesting, right?
But that statement, for it to be okay, you also need to prove to me that you actually use a polynomial, and then you go.
Yeah,
right.
That's like the key part, right? Because you construct the polynomial from the trace, right? And then the zero fire will divide that polynomial only if it's a real polynomial, right? From the trace, right? Because if the polynomial from the trace is not constructed as it was supposed to be constructed, then the zero fire will not divide that polynomial. Right?
Exactly.
Yeah. Then that's just details, right? Just then the Fry protocol.
Exactly, you got it.
I think I got it.
Now you have to code it.
Okay, let me show the code. Then
that's more difficult.
Yeah.
I mean, like the easy version isn't that difficult to code. In fact, probably it's easier to code than to understand. But then it kind of escalates because you have a lot of things. But let me show you. Let's try to see a bit the code. So these are benches. Yeah, I'm going to try to show the rounds, so how it works in the code. So you will see whether we have the improvers. We have Stark and Cairo. So this is a Star prover and this is a Cairo prover. If you have heard about Cairo is a VM that it's proven through Starks, but you can prove other things with Stark. Right now, we won't take a look at this Cairo thing. I think someone is trying to enter. For today, we will focus on the Star prover and don't care about.
Maybe the Fibonacci.
Yeah. So you will have a definition of constraints. For example, for tests, we use Fibonacci a lot, but you can have another one. So we will look for a function that must be called proof. Yes. So we are very creative with the name of the functions. And proof is the one you use to prove. And we have divided the protocol in rounds. You will see it in the documentation. So round 1, round 2, round 3, and so on. These rounds are not documented like this anywhere else. This is, we took this idea for Plonk. Plonk is documented as rounds, and to make it easier to understand, we also define our own rounds. So
yes, you're right. That's something we didn't mention, but we have originally interactive protocols between a prover and a verifier. But then what we do is we can like remove the verifier from the middle using this Fiat-Shamil heuristic. And so like replace the interactions between prover and verifier by the results of some hash function over the transcript of the protocol.
yeah, the idea there is that we are going to simulate the queries of the verifier. So what you will see in the code is that at some points, all the state gets committed to a structure that is called a transcript, and then it gets randomness, and the prover can't change that randomness because it has committed many values to it, and it can't change the values committed, so it holds. Of course, all the random parts that depend on a field element might break if you use a really small field element. That's why you shouldn't go there and naively change this for a Marcinus prime field or whatever, but that's how it works. So you will see this randomized error with preprocessing. This is a wrap. I won't explain wrap right now because it's another thing. I can tell it very quickly that there is some extra thing called a permutation argument that lets you prove that two things have the same elements. That's to say that two things are a permutation of each other, like two vector of elements. We can take a look at that later. But it goes at the beginning because it has an interaction with the verifier.
It's like constructing the trace with another interaction with the verifier.
Yeah, we can dig into that later. So every time that the verifier should challenge the prover to get some values or do something, you will see this function that kind of sample challenges. They are just random values, and the first one they will be used to what you showed to you. It had one constraint, but what happens when you have 1,000 constraints or a lot of constraints? Well, there will be a trick that is going to add them all together, like fold them, like you did in Fry with another random number.
Yes, that's called running the batched fry protocol. It's just doing like random linear combinations of many polynomials and showing that the random linear combination is a polynomial.
So this is the composition polynomial that is going to be the composition of, well, many polynomials. And if you take a look at how the composition polynomial is computed, you will see that it is the same. Oh, this is an abstract thing. Okay, I'm going. Let's get an overview and then we see how it works because it's dependent on the constraints. So this is round 2. Let's go back to proof. This is evaluation of the polynomial. You will see here. This is easier, so you have the composition poly and you evaluate it. Then you will see another round. Now Fry is going to start.
That round 3 is another optimization you have. So to prove consistency between the trace and the polynomial, you just take a point outside on D1, D0. You take like, okay, take some point at random from the whole field and evaluate there. And that what prevents is from doing some interpolation attacks because the prover cannot prepare in advance for any point over the domain. So that's why you have. Sorry.
No. Thank you. So this is Fry, a little bit of Fry-related code, and then we are reaching like the end. After this final step, the prover shows prepares like this proof and it's done. So there was some magic there at some point that I tried to show you, for example, how the composition poly is generated. Right now, that is defined in the airs. The airs are like the set of constraints that you use. So let me check.
We can show Fry perhaps because it's easier to look at the code of Fry.
Yeah, what things we can do? So Fry here you have the commit, and the commit is going to do the evaluation on the offset and generate a Merkle tree, which is this Fry Merkle tree that is actually a composition. I think is this the composition of Merkle trees? What is it? Okay, I might need it to. Oh, okay. You will see another optimization, but I don't know. Should I explain why do we have a batch Merkle tree? No, maybe not. No, this is going to be too good. Okay, don't worry about that. So let's see, for example, an error. This is Fibonacci. The simplest one should be this one. This is a simple Fibonacci. So this one is just a column that contains all the values of Fibonacci. So you have to have like to define this function that is how to compute the transition, and you will see that it is just one Fibonacci, like the third element is minus the second one minus the first one, that's 0. And it has some boundary constraints to say, okay, Fibonacci starts here. So this is, for example, the code. I don't know if there is. Well, this is a folding in Fry. Everything we have mentioned, it should be here, plus some other things. I don't know if you want to check anything in particular.
Yes, we have like all the documentation in the prover. You can go over it, and of course, if anything you don't understand anything, just tell us, and we'll try to improve the documentation. We want like to make this available for everyone. So
Maybe also start 101.
yes, we will add. I was also
Yes.
going to add that.
Nice.
So we will change a little bit the plan for this week. So we are focusing mostly on Starks, and also there was like a small group that wanted to start with multilinear polynomial and sound check. So if you want to deal with those topics, just let us know. So we kind of start working on these two big areas.
As a side note, we are currently working on the Star code. You will see some changes, probably in like 2 or 3 weeks. It should be stabilized. In particular, you will see that R definitions can be quite troublesome. So you would like to have an easy way to define an error. You will see Maiden did the R script. So, for example, Maiden invented its own language to define Earth that is called R script. We are working on doing something that is more comfortable. Right now, it's very manual.
And well, we will be talking about stars this week and looking at some things related to security and analysis. We will also be introducing some things related to hashes and that, but we thought it was like uh, fun to introduce this topic early in the bootcamp. And we know that many of you wanted to learn about this, so why not nearly from the beginning? And of course, now we are entering like phase two of the bootcamp. Do you have any questions? Something that you'd like to understand in more detail?
Yes, I want to take this opportunity to ask Mauro to run the prover, the Lambda works prover on a working
Ah,
example. You have that? How can I do that in my fork, right? On my side.
so you have two options. So if you want to run example on Star Prover, there is the integration test that kind of run everything. So that might enable you to play and say, okay, I want to make my own error that proves something. Maybe the example that Diego showed today, you want to try to implement that error, you can do it, and you should run it through the integration test, adding another one. The only prover on the stars that have a CLI to use is the Cairo prover. So you can use write some Cairo code. We have some commands on the main file to make it easier to prove. What is going to happen is that you have to compile the proof in proof mode. As I assume at some point we will explain what proof mode is and all that kind of things, but it's going to take a while. So it's going to compile the program, and then you are going internally it's going to run in the VM, generate a trace, and it's going to make a proof of that trace, and then you can verify it with another command. So I don't know what you want to write. I can show you how to do both of them, no problem. If you want, I can run like the integration test. The other thing is covered in the README too. Oh, here you will have, for example, this is, I think, a simple Fibonacci. You will see some constants that we define as proof option, like the blow-up, the blow-up factor. We didn't talk about the blow-up factor because that's more advanced, I think. Kind of the number of query, the cost that you were asking what the number should be, and the cleaning factor. So as an optimization, there is like a proof of work inside the code of the prover, so it's more expensive to try things. So that's the cleaning factor. But you said it there and be done. You set the public inputs. For example, this is dependent on the R. Fibonacci is going to say, okay, these are the starting numbers. You call proof with some R. You pass a trace. I think we have like a generator of a trace from Fibonacci. You pass all the parameters and a transcript. You will see that right now we are passing the Stone Prover transcript because we are making a transcript that is compatible with Stone. Maybe we will deploy another one that is more efficient later. And then you verify, and that's it. And hopefully this runs because we have a CI checking all the time that this runs, so it can't fail. And you can make your own. You will see a lot of errors because we are testing different things, like having many columns, shift the values. There is a quadratic trace. So,
Yes, it is. The example is coming.
And
and you have the ones with permutation arguments that this is for future.
And if you want to prove like programs written in Cairo, then you have to use the Cairo VM to generate the trace with proof mode, and then you can feed that to the prover
Yeah, we have integrated all the code, so you don't actually have to call VM by yourself, but you have to compile it in proof mode, or just use the commands that says that are written in the make file and it's going to work. I can show you that. We have a lot of programs here in Cairo. Cairo Lang, Cairo Prover. This is a strong prover. Now I want my prover. Our prover. Hours. So I'm going to go to main. We'll change make this. I don't have anything important, so I'm going to draw all my changes. Let's go to main. Pull the code. And then go to provers, the Cairo prover. And if you see the README, it tells you how to use this. You either need Docker or some dependencies. I'm not going to use Docker right now. Activate and I'm using fish. So I'm going to make. We have some compiled program, probably. But yeah. I'm going to compile some test programs that we have. I'm running the test, but the test actually compile the programs because it can't test without them. No, I don't need so many programs, so I'm satisfied. So I'm going to make proof, pass on program. Let's see if this one exists. Fibonacci, yeah, why not? We can send this one, for example. The proof, I don't care about it. It's going to compile, it's going to take a bit because it needs to run all the optimization. It is really slow. This actually the start proof compiles really fast, but right now we need to get the whole Cairo VM and lots of dependencies. They are more related to Cairo than to Starks. Well, after this compiles, it's going to work, and this is the integration test. You can see that it passed. You are free to add a test if you want to mess around. What happens if I change the trace and try to send something that shouldn't pass? Does it work? We have some tests like that. You can try to break the verifier. It's always good to have people trying to break the verifier.
Yeah, we also made some challenges with a broken prover, things that if you don't check in the prover or that you don't adjust the security level or whatever, you can easily.
Yeah, that's another thing. Like we wanted the security level to be easy to test. So right now I didn't set any security level. It's configured to 100 bits, but you have in proof options. You will see some enums that have predefined security levels. For example, depending on the how do you say the hypothesis, which well, depending how you do the proof, you have two ways of calculating the amount of security. One is conjecturable and the other is provable, and you can set it to the one you like. This is pre-generated, so you don't have to. If you want 100 bits, you just set it to this. It's like the right configuration. So let's see if this has compiled. It didn't. It's compiling Cairo Lang now. And Starnet, Curve, and Cairo Lang, Sierra Lang. This also has support for WebAssembly. If you have seen Stark Stack that Lambda works that Lambda did, you will see the brewer the verifier running online in a web server, verifying transactions of a blockchain. It was an experiment we did some months ago. It should run because it's all the dependencies are being there it goes, the Cairo VM. Yeah, it takes some time. I have like a PR to improve speed because
The optimizations.
yeah, we can drop some optimizations that are not being so useful just to avoid having to wait this long because they don't give any relevant speed up. At least I couldn't measure a speed up with them.
And to make it worse, our computers are not connected, so
So yeah, my Mac is trying to not drain all the battery when doing this. But it's soon going to be over. Just 3 more dependencies. The good thing is that it runs fast, but it doesn't compile fast. That's fast. There is, well, we should do a day of talk about the Cairo Brewer because it has like a lot of things. Proving a VM is not an easy task.
Yeah. And then we also have like some upcoming talks by other people.
okay, there it is.
Oh, there it goes. Whoops. It has made a proof.
Yes. There.
And so you have proof, and then there is make verify. I can send hopefully this, and it should verify. Verify. That's it.
Yeah, and verification is really fast and
Yes.
It probably can be faster. We will optimize it.
It's not fully optimized, not in terms of proof size, but still pretty decent.
Same with proving time. I mean, I'm sure we are going to do at least maybe 10 times more, make it 10 times faster.
Yeah, and we also want to add some optimizations using other protocols. So it's nice because we were doing things right now. Well,
Want to answer?
yeah, he's already in. I don't know if
Perfect.
you have further questions. I know maybe it was like a tiring session because there was like many things going on, but any other questions? I try to pass the photo of the.
Yes.
It looks better in the computer. I hope that when passing it over the phone, it didn't like degrade, but I can then break or something. Anything else? Well then, yeah, we will add also the documentation of Start 101 and everything so that you can start learning, and this will help us also deal with other proof systems, like we do with long, Block 16, those based on subjects. It will be like super fun. And don't worry if you don't understand it right now. Really, it took us like a very long time to understand everything. But at the end of the bootcamp, you really understand many things related to CKPs. It will be like awesome. So
Yeah, and you will get a good like overview of all the protocols. Maybe know what are the advantages and disadvantages of each, and make your own conclusions. See what you like more.
Yeah. So at least from our side, for today we don't have anything else. But of course, over this week we will have, as always, our sessions to discuss, and there we can go into more detail into different parts of the prover, the protocol, and then of course we will also start dealing with a small group that really wants to work on the topic, which is multilinear polynomials and subcheck, so that well, we get to learn and work on these new topics. Anything else?
I think Pat, you're talking, but I can't listen to you.
Oh, we can hear you.
Is there a minimum size for a field?
Yes, that's a very good question.
And a complicated one.
Now, but in general, you just need at least 500, 150 bits. Your field should have at least that
So
size.
you can see that at least, for example, each time that you ask for a random point or a random element, it's going to be as big. The amount of element for that random is going to be at most the amount of elements in the field, right? So if you make it too small, the randomness is not going to be enough. So your prover is going to get tracked. But you can actually still use a smaller field, as small as you want, as long as you have a field extension. Now you will start getting some flashbacks of maybe all the finite fields talks. So yes, but that changes the protocol a bit. It doesn't stay exactly the same.
Yeah. But we can one day talk about the security of Fry and the parameters and all that. I gave a talk, I think, two or 3 weeks ago on some aspects of Fry, so I can then also send you the link to the talk if you have some doubts regarding security. But really understanding the security proof of Fry is quite difficult because there are like many things of coding theory and other things, so it's like, okay. But it's a really nice protocol and quite elegant. It has like minimum cryptographic assumptions, so it's really good. Well, so from our side, I think we have like nothing else. And then, of course, see you in the next sessions to discuss more on Fry and other protocols and start coding these things. See you then.
See you.
Bye
Bye,
bye.
guys.
See you guys.
Very good.
This is